Hello, video on goodness of fit testing in the MEI S3 syllabus. I'm going to assume that you understand how to do the chi-squared testing, but I will go through and do some quick examples, and I'm going to focus on what the questions are asking us. So typically we have a large amount of text here explaining the context of what we're doing. We then have in every case they'll really give us the observed frequency. In most questions they'll give us the expected frequency, and then they'll ask us to carry out a hypothesis test on the goodness of fit and then to comment on the conclusions. The only variant on this is a question like this one here, where they gave us the observed values, but they didn't give us the expected values. They just told us that they're expecting the goodness of fit to be against a binomial distribution, and we have to go through and calculate those probabilities. But beyond that, then they go off and do the same thing and get us to do the test and do the calculations. Okay, so let's start with the first question. An amateur weather forecaster has been keeping records of air pressure. Here's a table of air pressure. She measures each day with a barometer and atmospheres. A random sample of her observations is summarized in the table below. So there's 100 random observations. That looks right, doesn't it? Because our observed frequency looks like we sum that up. Yeah, that's going to be 100. And then they're saying to us, the corresponding expected frequencies of a normal distribution with its two parameters estimated by sample statistics is also set out. So that's our expected, isn't it? F of E. But remember that they've estimated the two parameters, the mean and standard deviation. So we need to use those when we get to the degrees of freedom. So we know what our frequency observed and our frequency expected are. And what's it ask us to do? Carry out a test, a hypothesis test at 5% on the goodness of fit of a normal model. That's the one we've got there. And comment on your conclusions carefully. State your conclusions carefully and comment on your findings. There we go. So what's the first thing we've got to do in any of these? Goodness of fit, we need to set out our hypotheses, and our hypothesis is always that our distribution is a good fit. Yeah, normal dist good fit, and then our alternate distribution is purely that the distribution is not good fit, and we just need to do that and be done with it. Yeah, okay. And we know what our test statistic is going to be, because it's always in the same form. It's our frequency observed minus our frequency expected, all squared, over frequency expected. We do that for each class and we sum it up over all the classes. In this case we're starting with 7 classes. Okay. Now there's only one thing that's important to us here that will adjust what we're doing, and that our frequency expected value here, we need to have a value of greater than 5, because otherwise as its divisor it will muck up all our numbers and make them the test is unreliable. So we need to have values above 5. Now looking at here this example, our first 2 values here, there we go, and particularly this one at the top, our expected value is less than 5, so we're going to have to pull the results. And in this case we pull it with one that's similar, so we're going to pull the first 2. Yeah, so if we pull the first 2 classes, we've got observed frequency of 10 and the expected frequency, if we add those 2 together, of 6.68. yeah. So we're going to have to use that rather than the values. And rather than having 7 groups now, we've only got 6 groups. Okay, so for the examiner, what we want to do is to set out, to show that we know how to calculate our test statistics. So for the first group, group 1, so if I look at that, this is 1 and 2 combined, we would have 10 minus 6.68 all squared over 6.68, which equals 1.650. Okay, so that shows that we know how to calculate the test statistic contribution. Then we're going to show that we're going to sum them all up. So we could find each of the values here using the method we've just used, and we'd have 1.650, 1.774 for the second group, 3.230 plus 4.502 plus 0.402 plus 0.814. If we added that lot up, we're going to get a test statistic of 12.46. Okay, so that's the first thing we needed to do, and we just need to write that out so the examiner can see we know what we're doing. Well, now we need to find our critical value. Well, we find that from the chi-square distribution with the test statistic percentage and significance level that we're asked for, and our degrees of freedom. So we know here that we're on a 5%, we need our degrees of freedom. So degrees of freedom, let's have a look at where we are. So how many classes have we got now? Well, we started off with 7 classes, 1, 2, 3, 4, 5, 6, 7. We've pulled 2 of those together, so we've now got 6 classes, yeah? 6 classes. Then we have to take off the number of parameters that we have used the data to estimate. In this case, we estimated the mean and the standard deviation. And then we just got to take off 1 on the basis that we know that the total is 100. So we've already we've got a constraint there, haven't we? So we've used up 3 degrees of freedom. So we're left with 6 minus 3 is 3 degrees of freedom. Yeah. So now we can go to our tables. Let's have a look in our tables and see what we want. We want our probability to be, we want to use this right hand side here because we're looking at the right hand tail. We want a probability of 5% in that tail, so we're in this column here, second column of that side of the table, and we know we've got 3 degrees of freedom, so therefore we know that our critical value is 7.815. Yeah. So our critical value is 7.815. Okay, and if we look at our diagram here, the chi-squared, so we know our critical value is 7.815. And we already know what our test statistic is because we calculated that test statistic as being 12.46. So what are we saying here? We know our result is significant. Why is that? Because our test statistic is greater than our critical value. 12.46 there is greater than 7.815. So what are we saying about that? We have sufficient evidence to indicate that the normal distribution, we've got here, is not a good fit. Yeah. So that's the first part. Then they've asked us to comment. So we've reached a clear conclusion. Now they've asked us to comment on this. So what are we going to do? We're going to go and look at where the results are divergent. Let's have a look at where we had large contributions. So we had a large contribution, 4.5 there and 3.2 there. So that was let's have a look. So they came from these 2 groups here, didn't they? These 2 groups here, yeah. So that's because our expected values here are much larger than our observed values, yeah. So what we would comment on here, if you were asked to comment, I'd be saying the model overestimates the mid values, yeah? And you can put the ranges in there, and underestimates the end values, yeah? End values. So that's that one. And that's where you get your marks. You probably get a couple of marks there for comments, wouldn't you? And each one of those for the process. Okay, this one, second question, I'm going to do because it's got more workings to do. They're actually going to make you go through the process of calculating the expected values. But let's read the question as ever. In Germany, towards the end of the 19th century, a study was undertaken on the distribution of sexes of families of various sizes. The table shows that data about the number of girls in 500 families, each with 5 children. So here we go. So that's our frequency observed. And if we add that lot up, yep, that looks like it adds up to 500. So there were 32 families with no girls, yeah. It is thought that the binomial distribution, 5 children, some probability, should model these. Yeah. So they haven't given us those expected frequencies. Part 1, 3 marks for use this information to calculate an estimate for the mean number of girls per family of 5 children, and hence show that 0.545 can be taken as estimate for P. Good, so they've told us what the answer is as well that we're working towards. But let's try and work out what our P value is given the figures above. So looking at the figures above, we've got 32 families with no girls, so there's 0 girls in that group. We've got 110 families with 1 girl, so there's 110 girls there. 154 families with 2 girls, so that's 308 girls there. 125 families with 3 girls, there's 375 girls there. And 63 families with 4 girls, so there's there's 252 girls there. And finally, there are 16 families with 5 girls, so there's 80 girls there. So if we add that lot up, if we were looking to find the sort of average here, we know there's 1,125 girls there. Yeah. In the model answer, they want you to go, well, so if there's 120, so number 1, if there's 1,125 girls in 500 families, that means that in each family on average there's 2.25 girls. Yeah, that's their first point that they'd like to make. Makes sense, doesn't it? And then we have to work out what's the probability of a child being a girl. That's going to give us our P, an estimate of that. Well, if there's 2.25 girls per family on average, and there's 5 children in total in each of these, then that's divide one by the other, and we get the probability of being a girl in these families is 0.45, yeah? Because in effect that's 1,025 girls out of a total of 2,500 children, isn't it? And usually, just so you know, you'll see this thing P hat being written because we're using, and we've created an estimate for our P value, haven't we, here? That's what we're going to use. So there's our 3 marks for finding an estimate of our P value. Okay, what's our next step? Next part of this is they want us to investigate at 5% whether the binomial model with P equals 0.55 fits the data, and then comment on our findings, comment on your findings, on the extent to which the conditions for a binomial are likely to be met. Okay, so what I want to do, I need to find my probabilities and I need to find my expected frequencies, don't I? So let's have a look at how I'm going to use this. What I need to do is, I've now concluded that I'm working with a binomial with 5 children per family, and the probability of being a girl is 0.45. So I can therefore find my probabilities for probability of x equals start with 0 and then 1, etc. I need these values, don't I? So I'm going to use my calculator to do that, and I'm going to use a binomial. So I can go into my binomial, I can say I want to have 0 successes from 5 trials with a probability of 0.45 of success. So probability of having no girls is therefore 0.50328, yeah? So you can go to the calculator, yeah. So if that's the probability in each one, when my expected value in 500 families is going to be 500 times that number, isn't it? 0.503287, and I'm going to get a number around, if I calculate that out, I'd get 25.16. So I'd expect 25 families to have that, to have no girls, yeah, if it's binomial. And of course, my next point, and I can go through, I put a table together here with those calculations, yeah. So here's my table, here's my number of girls here. Here's my actual, the observed frequency. Here's the probabilities, which I could get from a binomial. So if I wanted to get the next one up, this one here, then I can go to my calculator, can't I? And I can change. So my X is going to be 1 girl now out of 5. Gives me my 2.059, yeah? Multiply that by 500 and I get my expected frequency. And what am I going to do? Then I need to calculate my contributions. So I just want to show that I know how to do that. So I'm going to do my TS of my first group, which is going to be my frequency observed is 32 minus 25.15 squared over 25.15, and that will equal our 1.8. If I put that in my calculator, I get 1.866. So I go down and complete a table like that for the examiner so they can see what I'm doing. And then I need to know what my test statistic is. Well, my test statistic is going to be my total of my contributions. And in this case, if I sum up those contributions I've just calculated, I'm going to have 10.52. There we go. Okay, now I need to find my critical values. Okay, and I'm getting that again from my chi-squared distribution. I need my percentage of my significance level, and I need my degrees of freedom. So let's have a look. Degrees of freedom. Well, how many classes did I have? I had between 0 and 5 girls there, so I've got 6 classes. How many parameters have I estimated? Well, I've estimated 1 because I had to go and find my p hat to do the calculation, and then I also lose a degree of freedom because I know there's 500 in my total. So my degrees of freedom here are 4, and if I go to, and with my significance level of 5% again, degrees of freedom of 4, I can see that my critical value is 9.488. So let's go back then. So my critical value is going to be 9.488. If I draw my diagram, my chi-squared, I now know my critical value is 9.488. I know my test statistic is 10.52. So I know my result is significant. Why? Because my test statistic is greater than my critical value. Okay, so there's sufficient evidence to indicate that the binomial is not good fit. Yeah. So that's my conclusion. Yeah. Then they've asked us to comment on the result, taking into account the assumptions. So before I do that, I'm just going to go back actually and see where it diverges. So let's have a quick look at where my contributions come from, big contributions come from. So here's my biggest contribution here, 4.97, and that's for my 5. So they expected to have a 9 families with 5 girls, and they actually had 16. So that's the biggest of all, isn't it? And it's going the other way around in the middle here again, isn't it? So I would start by, so my final comment on the data would be that the binomial model is overestimating number of families with 5 girls. Yeah, 5 girls. That asked us to comment in relation to binomial. Well, what do we know about binomial assumptions? Well, we know that we must have the same, P must be constant, and our other one is that the trials are independent. Yeah, those are our 2 big ones, aren't they, for binomial? So what can we say about this? That these assumptions not being met, yeah, not being met in the population. So either P is not constant or the trials are not independent. Be interesting to know which, wouldn't it? If there were any demographic trials on that. Okay, so here's our final comments then. So on these tests, we know what we're doing, don't we? We're going to calculate our test statistic here using that format from the data we've got. So we need our observed frequency and our expected, and we sum them up to get our test statistic. We then go and get our critical values from the chi-squared distribution. We need our significance level, and we need our degrees of freedom. And we calculate our degrees of freedom from the number of classes. Then we've got to deduct the number of parameters we've estimated, because we've used up those degrees of freedom, and then we've got to deduct 1 for the fact that we've used a degree of freedom because we know our total, our sum is our sum. Yeah, there's 500 in our sample. We then need to, in these exam questions, to comment on which of the high contribution classes. So that tells us where the model's under or overestimating, and any assumptions not being met. So like we just did in the binomial, but we could do the same in a normal or Poisson. You know, what assumptions are not being met. So there we are. Hope that's of use to you, and best of luck.